So we start our topic vectors, vector algebra, chapter 10. Actually, what is a vector quantity? A quantity that has both magnitude as well as direction is called a vector. And if it is not a vector, quantities that are not vectors are called scalars. So, for example, force. Force when you apply, how much force and which direction. So it has both magnitude and direction. That is a vector quantity. But if you take time, you may say how much time, but you cannot say in which direction. So time is a scalar quantity. Volume, you can say how much volume. There is no question of in which direction. Volume is a scalar quantity. Displacement, you can ask which direction and how much. So displacement is a vector quantity. Similarly, work done, you can say how much work is done, but work doesn't have a direction. So it is a scalar quantity. So time is a scalar quantity, volume is a scalar quantity, displacement is a vector quantity, work done is a scalar quantity. Okay? We consider in our discussion that set of all real numbers is considered as scalars, members of R, real numbers. Well, a directed line segment can represent a vector. A directed line segment has an initial point and terminal point. There is a direction. And is it a line segment? It has a quantity, it has a length. That's why it can represent a vector. A directed line segment is a vector, or it can represent a vector denoted by, suppose initial point is A, terminal point is B, it is denoted by periodic vector AB. There is an arrow above A. Vector AB also I can just denote by a small simple A. Vector A. We can read it vector AB or vector A. Okay. A is initial point, B is terminal. You can simply denote by vector A or vector AB. The distance between A and B is called the magnitude of the vector and is denoted by, we read it magnitude of AB, or simply number A or magnitude of vector A. Even if we simply say AB without arrow, it also represents the length AB. The arrow indicates the direction of the vector. The vector space R3, we know R3 is R cross R, which is the set of all ordered triplets X, Y, Z, where X, Y, Z are real numbers. Position vector. Now, suppose P is a point in space whose coordinates are x, y, z. Any point in space has three coordinates x, y, z. If P is a point in space whose coordinates are x, y, and z, then the vector OP, where O is the origin, is called the direction. O is the origin, we know is O00. Is a position vector of P. The position vector of P. OP, vector OP is called the position vector of P. Also, we get the length of P, by distance formula, under root x squared plus y squared plus z squared. Okay? That is called the magnitude of the vector OP, denoted by magnitude of vector OP. We can also simply write OP, that is nothing but under root x squared plus y squared plus z squared. X coordinate, this y axis, z axis, three-dimensional. P is any point in the space P, X, Y, Z. Direction angles, direction cosines, and direction ratios, very important points. Suppose P is any point and OP is the position vector of the point P. Remember, when P is a point in R3, vector OP is called the position vector of the point P. Position vector simply means the vector due to the position of the vector point P. Position vector of the point P, that is vector OP. And the angles made by this vector R with OX, OY, OZ, which we respectively denote by alpha, beta, gamma. So angles alpha, beta, gamma made by the vector R with the positive direction of x, y, and z axis respectively, called the direction angles of the vector r. Direction angles of the vector r, alpha, beta, gamma. Okay, and their cosines, that is cos alpha, cos beta, cos gamma, are called the direction cosines, which we usually denote by L, M, N. L is cos alpha, M is cos beta, N is cos gamma. They are known as direction cosines. What is alpha, beta, gamma? Angles made by the given vector with OX, OY, OZ. L, M, N. L equal to cos alpha, M equal to cos beta, and N equal to cos gamma. Now, if ABC are three numbers proportional to L, M, and N, then ABC are called the direction ratios. There could be any numbers which are proportional to this. Direction ratios of the vector R. Here X will be LR. We can even say A will be, if P is XYZ, then we can easily come to the conclusion X equal to LR, Y equal to MR, and Z equal to NR, where R is representing the magnitude of the vector. Okay, we have P, X, Y, Z. We can easily show P. What is, I have drawn only the foot of finger of P on OY. So cos beta will be Y by OP, that is Y by R. Y is equal to cos beta into R, that is Y equal to MR. Y equal to MR. So you can easily observe that X equal to NR, X equal to LR, and N, Z equal to NR. So X equal to LR, Y equal to MR, and Z equal to NR. Okay, and L squared plus Y squared plus Z N squared, L squared plus M squared plus N squared. It is nothing but what is L? X by R. X by R squared plus Y by R squared plus Z by R squared. You can easily see it is nothing but X squared plus Y squared plus Z squared by R squared. But what is R squared? R squared is again X squared plus Y squared plus Z squared, that is equal to 1. So it's a very important point to remember for direction cosines element for any line or any vector. L squared plus M squared plus N squared is always 1. Point to remember. If L, M, N are the direction cosines of any vector, then L squared plus M squared plus N squared will be always 1. But not generally for the direction ratios. Not A squared plus B squared plus C squared need not be equal to 1 in general. The type of vectors. Zero vector, vector having initial point and terminal point coincides, or it has magnitude 0 and it has arbitrary direction or no direction. A vector whose initial point and terminal point coincides is called a zero vector. Okay, or a null vector denoted by 0 with vector symbol. Zero vector. Zero vector has magnitude 0 and and cannot be assigned any direction, or alternatively we can say it is regarded as having arbitrary direction. You can assign any direction, or cannot say it has a specific direction. It has arbitrary direction. Okay. Unit vector. Unit vector is a vector having magnitude 1. Okay. Unit vector in the direction of A. In the direction of a vector A is usually denoted by a cap. And is a cap represents unit vector in the direction of A. Co-initial vectors, obviously two or more vectors having same initial point are called co-initial vectors. Same initial point. Okay, same initial point. All have same initial point. Collinear vectors. Two or more vectors are said to be collinear if they are if they are parallel to the same line, irrespective of the magnitude and direction. That means there may be a different direction. That means maybe this direction and maybe opposite direction. But parallel to a line, they are collinear vectors. May have different magnitude, maybe bigger or smaller, maybe same direction or opposite direction, but they are parallel to a line. They are called. That means they will be in same direction or in the opposite directions. Equal vectors. Two vectors are equal if they have same direction and the same magnitude. Two vectors A and B are said to be equal if they have same magnitude and same direction, regardless their positions of their initial point. Even if you have different positions, different initial vectors, different terminal vectors, but if they are in same direction and the same magnitude, they are called equal vectors. Negative of a vector. A vector whose magnitude is same as that of a given vector whose direction is the opposite direction is called the negative of the given vector. Vector BA and AB are negative of each other. We can even write BA equal to minus AB. All these defined here may be subject to its parallel displacement. A vector, this is a vector, and even if you have a parallel displacement like this, same vector, they are same. It is irrespective of their initial point or terminal point. Without changing the magnitude and direction, if you make a parallel displacement, they are same vectors, and we can call them free vectors. In this chapter, we are dealing only free vectors. Represent graphically a displacement of 40 kilometers 30-degree west of south. Remember, this you have north and south. This will be usually north, and you have south, and 40 kilometers 30-degree west of south. West of this is west, 30-degree west of south, 30 degrees, and we have length 40 kilometers. 40 kilometers 30-degree west of south. Okay, 40 kilometers 30-degree west of south. How do we represent? Here the vector OP represents the required displacement. We are only asked to represent. Okay. In the following figure, I am giving a square very specifically. Identify co-initial vectors. Can you tell me co-initial vectors? This vector, I have four vectors here: A, B, C, and D. Vector A, this is vector A. The direction is here. Okay, and vector B, the direction is here. Vector C, the direction is here. Vector D, the direction is here. It is obvious from here. It's given the direction. Co-initial vectors you can easily observe A and D. Equal vectors, you can even go on telling equal vectors. B and D are equal vectors. Negative of each other. A and C are negative. Collinear, but not equal. B and D are collinear and equal. So A and C itself are collinear but not equal. I think that's done. Equal vectors, negative of vector, collinear but not. Okay. Now addition of two vectors. We have two laws here. One is mainly triangular law of vector addition. That means if two vectors can be represented as the two sides of a triangle in the same order, the magnitude and in magnitude and direction, then the addition of these two vectors can be represented by the third side of the triangle in magnitude and direction. Simple one. If you have vector A and B, if I am going to represent this as two sides, look at same length, same direction, but displaced A and B, then the A plus B will be the third side of the parallel, the triangle. This will be A plus B. Okay? A plus B. That is a law of triangular conjunction. Or AB plus BC is AC. Very important you have to remember. Always AB plus BC is AC. Parallelogram law of addition. Parallelogram law, you know it. If two vectors can be represented as two sides of a parallelogram with same initial point, then in magnitude and direction, then their sum will be represented by the diagonal of the parallelogram with the same initial point. This diagonal. If you have vector A and vector B, then this will be A plus B. For A and B, two adjacent sides of parallelogram, their sum is represented by the diagonal with the same initial point in magnitude and direction. OA plus OB is OC, where OACB is a parallelogram. OACB is a parallelogram. We can extend it the triangular law to polygonal law of addition. We can easily see that parallelogram law and triangular law are one and the same. Polygonal law of addition. In a polygon ABCDEF, AB plus BC plus CD plus DE plus EF is A. You observe AB, BC, CD, DE, and EF. Their sum will be nothing but AF. The sum will be AF. Subtraction of vectors. A minus B, you can write A plus minus B. This is A, this is minus B, A minus B. And A plus B. B is here, A plus B. A plus B and A minus B, you can easily identify. Properties of vector addition. A and B are vectors, then A plus B is also obviously a vector. It's commutative, right? It's associative, vector addition is associative. And you can see that 0 vector is additive identity, A plus 0 is A, and A plus minus A is 0. Simple properties. Multiplication of vector by a scalar. If A is a vector and lambda is a scalar, then is a vector. Lambda into A is a vector. So that lambda and lambda A are in the same direction if lambda more than 0, and opposite direction if lambda less than 0. Remember this point. Lambda A will be 0 vector. Lambda A will be 0 vector if lambda is 0. Lambda A will be 0 vector if lambda is 0. 0 vector. Mod lambda is, or magnitude of lambda is mod lambda into magnitude of A. Magnitude of lambda is modulus of lambda into magnitude of A. Now A, if you have 2A, twice the length, same direction. If it is if it is half A, half the length, same direction. If you have minus A, same length, opposite direction. Properties of scalar multiplication. Obvious properties. Of course, we have lambda A is a vector that is specified. Further, lambda into A plus B is lambda A plus lambda B. Lambda plus beta into A equal to lambda A plus beta A. Lambda beta into A is lambda into beta A. 1 into A equal to non-zero vectors A and B are in the same direction if A is equal to lambda B, where lambda more than 0. There is a lambda more than 0, so that A is equal to lambda B. In opposite direction, if there is a lambda less than 0, so that A is equal to lambda. When can you say they are in different direction? If there is no lambda, where lambda A is equal to lambda. Okay, take care of this point very importantly. And this question represent graphically, only graphically you can easily find. And in this is a regular hexagon. Remember, it's a regular hexagon. You can easily identify vectors which are coinitial, equal, negative of each other, collinear but not equal. Well, stage 2 and 4, true or false. We will do it. Meet back for the next class. Okay.